Hi everyone, my name is Seung-Jae from Pukyong National University. Today I will talk about my presentation on Conference of Disaster Mitigation Technology for the Smart Infrastructure. Today my topic is mathematical experiments for parameters of microplastic settling velocity. The presentation will be conducted in the following order. The first content is introduction, second the method, third is result, and the last is discussion. So this is the introduction. As the use of plastic increases, the amount of plastic released into the ocean increases. Released plastic drifts into the ocean and decomposes into microplastics, which cause various environmental problems such as marine warming, ecosystem destruction. This problem can be solved through behavior prediction using the settling velocity of microplastics. To date, many studies are underway to collect plastics drifting on the ocean, but there is a lack of research on microplastics. One of the most important factors for predicting the behavior of microplastics is the settling velocity of particles. However, the formula previously developed to predict the settling velocity of microplastics can only be applied to certain shapes. The settling velocity prediction formula, which can only be applied to certain shapes, can exhibit high errors in predicting hotspots of plastic drifting in the ocean. Therefore, this study aimed to establish a settling velocity prediction formula that can be applied to various shapes of microplastics. In fact, it takes a lot of time, manpower, and budget to collect samples of microplastics present in the ocean and conduct settling velocity experiments. Therefore, we conduct an experiment by printing various particles that could exist in the ocean with a 3D printer. When particles with various shapes are output to a 3D printer, they are greatly shortened in budget and time, and more accurate information can be obtained based on a large amount of data. The particles used in this experiment were modeled under various conditions, shape, size, and density. Using a 1-to-3D design 3D modeling software. It can be found in Figure 1. The particle has two shapes, sphere and pyramid. The reason why the two shapes were adopted is that they were judged to be the basis of all shapes, and more shapes will be printed to collect data in the future. Sphere and pyramid particles were modeled for 14 types with different diameter and different lengths of one side respectively. And total of 56 types of particles were produced using two liquid resin with different densities. So this figure shows the schematic of the experiment. The settling experiment was conducted in a small acrylic water column made of 200 millimeter times 200 millimeter times 400 millimeter. The entire process were recorded at 125 fps using a high-speed camera. So this figure 3 shows the results. When you see the left side of the figure, you can see the result recorded by the high-speed camera. In the image recorded at 125 fps, the location information of the particle was calculated through pixelization in the MATLAB as follows. And the final particle settling velocity was calculated through time and direction informations. And I will introduce about the Dietrich's settling velocity formula, which was previously developed and used to predict the settling velocity, was used as a theoretical value to compare the experimental values. To calculate the settling velocity from the data expressed in the CD and Reynolds space, the difficulty of defining the cross-section area of a particle can be solved through coordinate transformation. From dimensionless velocity and diameter, they derive R1, R2, R3 as fitting equation for size and density as R1. R2 is a fitting equation for shapes, and R3 for roundness fitting equation respectively. Finally, W star with the red box is equation that used as a theoretical value in this study. And this is the result for settling experiments. As you can see on the figure, the larger the density and size of the spherical particle, the closer to trajectory was to straight line. The pyramid shaped particle settled in a trajectory that rotate and repeated curves. The settling velocity was faster for pyramid-shaped particle in the same volume, density, and mass than for spherical particles. It is judged that the cause of the speed difference is the formation of drag and turbulence according to shape, excluding volume, density, and mass. The drag is affected by a single area perpendicular to the direction of motion of particle, while spherical particle settle in a certain cross-section area. Pyramid-shaped particles rotated and continuously changed their cross-section area, settling and turbulence generated by the angle between the vertex and the plane are also believed to affect the settling velocity of particles. So, comparing the theoretical and experimental values, difference occurs at the same densities. The experimental value was faster than the theoretical value, and the same pattern was shown in the two types of densities where the experiment was conducted. Since the settling velocity formula adopted as the theoretical value is an empirical formula for natural predicate, it is judged that the spherical particle used in this experiment and the shape limit make the difference in settling velocity. So this is my conclusion. This study was conducted with the aim of establishing settling velocity prediction formula, which is basis for predicting the behavior of microplastic drifting in the ocean. At the same density, volume, and mass, primed particles settle faster than spherical particles. And the figure 5 shows that the Dietrich settling velocity formula cannot be applied to particles with various shapes. Therefore, it is necessary to establish a new empirical equation that can predict the settling velocity for various particle shapes. So this is end of my presentation. Thank you for listening.